Some nights you look up and the sky seems very still. The stars are there, the way they always are, quiet, patient, burning slowly in a darkness that has no edge you can see. You might not think about them much. Most people don't. But they're always there, doing something enormous and doing it without any urgency at all. There is one star that matters most to you. You have never really looked at it directly. It's too bright for that. It hangs above every day of your life, and you have never once introduced yourself. It is, of course, the sun. And the sun, this warm, steady thing, is not permanent. It never was. Somewhere deep inside it, a slow countdown has always been running. Scientists have studied it for a long time now, and they have built a picture of what the sun's story looks like from beginning to end. What it has already been through. What it is doing right now quietly, without anyone asking. And what it will eventually become. That story takes a very long time to tell. But tonight, we have time. There's no rush. There's nowhere else to be. So if you'd like to stay for a while, just rest here, close your eyes, and let the sound of this carry you somewhere gentle. You're welcome to stay as long as you like. Now, let's drift. The sun is old. Not old in the way a building gets old or a mountain slowly wears down, but old in a way that is genuinely difficult to hold in your mind. Scientists have calculated its age at roughly 4.5 billion years. That number floats in the brain for a moment and then sort of dissolves because it's too large to feel real. Here is one way to try to feel it. If you compress the entire history of the sun into a single year, each month would represent about 400 million years. The Earth itself, this planet, everything on it, every ocean and forest and footprint would not arrive until around September of that year. And humans, our entire species, everything we've ever built or said or felt would appear somewhere in the final half-second of New Year's Eve. The sun in that picture has been burning quietly since January 1st. Researchers who study stellar evolution, the life cycles of stars, have found that our sun belongs to a category they call G-type main sequence stars. The name sounds technical, but what it means is reassuringly ordinary. The sun is a middle-aged medium-sized star, doing exactly what stars like it are supposed to do. It burns. It holds its shape. It radiates warmth outward in all directions at once without discriminating. At its core, a place so hot and dense that no human technology could survive there for even a fraction of a moment, a process called nuclear fusion has been running continuously for all those billions of years. Hydrogen atoms are pressed together with such enormous force that they merge and become helium. And in that transformation, a tiny amount of mass converts into energy. That energy works its way outward through layer after layer of the sun's interior, bouncing and scattering and slowing. And eventually, after a journey that can take tens of thousands of years just to escape from the core, it reaches the surface. It becomes light. It crosses the 93 million miles of space between the sun and Earth in about 8 minutes. And then sometimes it falls quietly on a face that is tilted up toward it on a warm afternoon. Scientists suggest that the sun loses mass, constantly converting about 4 million tons of hydrogen into energy every single second. That sounds enormous, and it is. But the sun contains so much hydrogen that this process can continue for another 5 billion years before the supply runs low. 5 billion years. There is something gently strange about that number. Not frightening, just very, very patient. The sun is not hurrying toward anything. It is simply doing what it has always done at the pace that physics requires. In that sense, it is one of the calmest things in existence. Astronomers have built detailed models of the sun's structure, not by looking at it directly, but by studying the sound waves that pass through its interior. The field is called helioseismology, and it works something like the way a doctor might listen to a patient's breathing to understand what's happening inside. The sun vibrates at frequencies too low for human ears to hear, but sensitive instruments can detect them, and from those vibrations, researchers have built a detailed picture of what lies beneath the surface. What they found is that the sun is layered in ways that are not obvious. The outermost region, where convection currents carry hot plasma upward and cooler plasma sinks back down, looks something like an enormous boiling pot if the pot were 1,000,000 miles wide and the bubbles were the size of entire countries. Beneath that, a deeper zone where energy moves more slowly by radiation rather than convection. And at the center, the core, a place smaller in proportion to the whole sun than you might expect, but containing the engine that has powered everything. Researchers have also found that the sun has moods in a sense. It goes through 11-year cycles of higher and lower activity, during which the number of sunspots on its surface rises and falls. Sunspots are regions of intense magnetic activity, slightly cooler than the surrounding surface, which makes them appear darker by contrast. During periods of high activity, the sun sends more charged particles streaming outward into the solar system. When those particles reach Earth, they interact with the upper atmosphere and sometimes produce the aurora, that soft, slow shimmer of light in the northern and southern skies that people travel great distances just to stand beneath. The connection between the sun and those lights, stretched across 93 million miles of empty space, is not obvious, but it is real. The sun is more entangled with everything around it than it appears. At its surface, the temperature is about 5,500 degrees Celsius. That sounds very hot, and it is. But the sun's outer atmosphere, the corona, the thin, ghostly halo of plasma that extends millions of miles beyond the visible disk, is somehow far hotter than the surface beneath it. Scientists are still exploring why. It remains one of the more persistent mysteries in solar physics. The energy seems to be there, moving in ways that models don't yet fully explain. The sun, after all these centuries of study, still holds things quietly to itself. For now, though, it continues. Hydrogen into helium. Helium settling in the core. The same process, the same slow rhythm, day after day, year after year, for billions of years, that no human mind has ever truly been able to hold all at once. But stars do not burn forever. Astrophysicists have traced the future of the sun with careful, patient calculation, and what they have found is this: sometime around 5 billion years from now, the hydrogen at the core will begin to run low. Not all at once, slowly, the way a candle dims before it goes out. The core will have been burning hydrogen for so long that what remains there is mostly helium, the ash of fusion, inert and patient, waiting. When the hydrogen in the core is gone, something shifts. The fusion that has been holding the sun's weight up against gravity will slow. And in that slowing, the core will begin to contract, pressed inward by the enormous weight of everything above it. As it compresses, it heats up, and that heat radiates outward into the layers surrounding the core where hydrogen still exists, and there a new shell of fusion ignites. What happens next is one of the stranger chapters in the sun's story. As this shell fusion begins, it generates more energy than the core fusion did before. The outer layers of the sun, the vast envelope of gas that makes up most of its volume, begin to expand. Slowly at first, and then more and more as the energy pushes outward against less and less resistance. The sun grows. Scientists call this transition the red giant phase. The name is both accurate and insufficient. The sun will not simply become a slightly larger version of itself, it will become something almost unrecognizable. Over millions of years, its outer atmosphere will expand until it reaches somewhere close to the current orbit of the Earth. The disk that hangs over the horizon every morning, that small bright circle of light, will one day fill a significant portion of the sky, glowing a deep burnished red, because as it expands, its surface cools. Cooler plasma glows red rather than yellow-white. Researchers studying stellar evolution have modeled this process in considerable detail. They've found that the expansion is not a smooth, steady thing, but happens in periods of relative stability, punctuated by thermal pulses, episodes where helium in the shell ignites in a flash, then settles, then ignites again. Each pulse releases an enormous amount of energy and causes the outer layers to swell further outward. There is something almost meditative about imagining it, this enormously slow expansion over timescales that dwarf anything human civilization has ever known. The sun growing larger by amounts that would be impossible to detect over a human lifetime, or 1,000 lifetimes, or 10,000. Change happening at a pace so vast that the very concept of watching it seems almost meaningless. By the time the sun reaches its maximum size as a red giant, the inner planets of the solar system will be in an environment nothing like what exists today. Mercury will be gone, engulfed long before the expansion reaches its peak. Venus too, most likely. Earth's fate is less certain. Some models suggest that as the sun loses mass during this period, Earth's orbit will drift slightly outward, potentially enough to escape. Other calculations suggest otherwise. The uncertainty is genuine, and scientists who work on this are honest about it. What is not uncertain is that life on Earth as we know it will have ended long before the sun becomes a red giant. Not because of the expansion itself, but because of subtler changes that happen much sooner. As the sun gradually brightens over the next billion years or so, a natural part of its evolution, even now, the oceans will slowly become too warm to remain liquid. Researchers suggest this will happen somewhere between 1 and 2 billion years from now. On the scale of the sun's full lifespan, that is not so far away, but 1 to 2 billion years is still an almost incomprehensible span of time. Life has existed on Earth for roughly 3.5 billion years. In that time, it has moved from single cells to everything that exists now. What another billion years might produce, given the pace of biological change, is not something any model can easily predict. For now, though, the Sun is stable. It is burning its hydrogen steadily, at a rate that will sustain this warmth for another 5 billion years. The expansion is not near. It is out there somewhere in the future, patient, the way the Sun itself is patient. During the red giant phase, something else happens quietly alongside the expansion. As the outer layers of the Sun are pushed outward and eventually escape entirely into space, carried away on an increasingly powerful stellar wind, the material that was once the Sun's atmosphere will drift outward in a slowly expanding shell of glowing gas. Astronomers call this a planetary nebula. Though it has nothing to do with planets, the name is historical, a relic of when early observers, looking through small telescopes, saw these objects and thought they looked vaguely like the disks of planets. A planetary nebula is one of the more beautiful things in the universe to photograph. The images show shells of gas in colors that seem almost too vivid to be real blues, purples, reds, soft greens glowing, because the hot remnant at the center ionizes the gas and causes it to fluoresce. Some of these nebulae are spherical. Others are shaped by magnetic fields or the motion of the star through space, and they form rings, hourglasses, butterfly shapes, spirals. Each one is unique. Each one is the final breath of a star that burned for billions of years. The Sun will make one too, eventually. Far in the future, someone or something, if anything exists to look, might see it from a distance as a faint ring of light in the sky, centered on a small, hot, fading point. What is left after the planetary nebula drifts away is called a white dwarf. It is not a star in the way the Sun is a star. It is not burning. It is not generating new energy. It is instead the core that remains after all the outer layers have been shed, compressed, dense, extraordinarily hot, but no longer fueled by fusion. It is the memory of a star still radiating the heat it accumulated over billions of years. Astrophysicists have studied white dwarfs extensively. What they've found is that a typical white dwarf is roughly the size of Earth, a sphere about 12 or 13,000 kilometers across, but with a mass close to that of the Sun. The density that implies is almost impossible to translate into anything familiar. A teaspoon of white dwarf material researchers have estimated would weigh roughly 5 tons. Not because of any exotic physics, but simply because so much matter is packed into so small a space. The atoms themselves are still intact, electrons still orbit nuclei, but they are pressed together far more tightly than anything in ordinary experience. What holds a white dwarf up against its own gravity is a quantum mechanical effect called electron degeneracy pressure. The electrons inside the white dwarf, packed so close together, resist further compression, not because of heat or gas pressure as in an ordinary star, but because of the fundamental rules that govern how particles can occupy space. It is, in a sense, quantum physics holding the remnant of a star in shape for billions of years. The Sun's white dwarf will form from the carbon and oxygen core that builds up during the helium-burning phase of its red giant life. When the outer layers have been expelled and the nebula has drifted outward and faded, what remains at the center will be this dense remnant, glowing at an initial temperature of perhaps 100,000 degrees. Over time, enormous amounts of time, it will cool, slowly giving off the heat it accumulated, slowly fading from white-hot to yellow to orange to red, and eventually, in theory, to a cold, dark object that radiates almost nothing. This final state is called a black dwarf. No black dwarfs are believed to exist yet anywhere in the observable universe. The universe is not old enough, not even close. The cooling process takes longer than the current age of the universe, which is itself about 13.5 billion years. A black dwarf is in that sense a purely theoretical object, a prediction of physics that has not yet had time to come true. There is something gently humbling about that. The universe, old as it is by any human measure, is still too young to have produced its own remnants. The white dwarf stage is long, very long. Astronomers estimate that even after billions of years of cooling a white dwarf, the mass of the Sun's remnant will still be giving off faint heat. The energy that was gathered across a lifetime of fusion does not disappear quickly. It disperses very slowly into the surrounding space. There is a particular kind of white dwarf that astronomers have found especially useful, not for what it is, but for what happens to some of them. In binary star systems, where two stars orbit each other, a white dwarf can sometimes pull material from its companion star if they are close enough. Over time, this accumulated material builds up on the white dwarf's surface. When enough has gathered, it can ignite in a sudden burst, a nova, a flash of light, visible from great distances. In rare cases, if enough mass accumulates to push the white dwarf past a certain threshold, the entire object detonates in a type of explosion called a Type 1, a supernova, one of the most energetic events in the universe, briefly outshining entire galaxies. The Sun will not do this. It will end its life alone, or with no companion close enough to matter. Its white dwarf will simply cool, quietly, over timescales that have no human equivalent. Astronomers have found many white dwarfs in the sky. Some are nearby. The nearest Sirius B is less than 9 light-years away, a companion to the brightest star in the night sky. Others are in clusters, groups of stars that form together and evolve together, offering a kind of snapshot of stellar aging that researchers have used to refine their models of how stars live and die. Each white dwarf in the sky is a story that has already reached this chapter. Each one is the remnant of something that was for billions of years, much like the Sun, burning its hydrogen, holding a system of planets in careful orbits, perhaps somewhere in the universe's long history, warming a surface where something like rain once fell. We cannot know that. The white dwarfs are quiet now, and yet there is something that does not feel like loss in that quietness, more like a settling. Like the way a fire does not disappear, it becomes warmth that spread through a room, and then through the air, and then into the night, and the night carries it somewhere else entirely. The energy does not vanish. It disperses. It becomes part of the larger, slower system of things. The atoms that were once the Sun, the carbon and oxygen in the white dwarf, the gas in the planetary nebula, those atoms will drift. Some will be caught by the gravity of other systems. Some will be incorporated into new stars, new planets, perhaps eventually new oceans and skies. The material moves. Only the shape changes. Scientists who study the deep future of the universe have traced these paths as far as physics allows. Long after the Sun has become a cold remnant, Long after the Milky Way has merged with its neighboring galaxies, the universe will continue different, slower, darker, but continuous. There is no ending exactly, only change. And tonight, the sun is still there, doing what it has always done, burning its hydrogen into helium steadily in a core that will not run low for another 5 billion years. The light crossing all that distance right now, landing softly on the darkened side of the Earth, where it is night, where most of its warmth is stored in the ground and in the air, and in the slow breathing of things that are resting. You are in a way made of stars, not metaphorically, literally. The carbon in your cells, the oxygen you are breathing, the calcium in your bones, all of it was forged in the cores of stars that burned out long before the sun existed and then spread through space and eventually gathered here. The universe recycled itself into you. The sun will one day give its own atoms back as well. Slowly, gently in the way, all things return to something larger. For now, though, it is still here, still burning, still warm, and for tonight at least. So are you, somewhere quiet, somewhere dark, somewhere the world is very still. Let that be enough.